Very good. So, yeah, it's been a wonderful week. This conference has been devoted to proof assistant technology, symbolic automated reasoning, and machine learning and neural methods. So, Aina Niemetz, the next speaker, works in the body of symbolic automated reasoning, which in the last couple of decades has not only had impacts on tools for mathematical reasoning, but even more, it's been totally transformative in software, hardware, and software verification. Could you tell us about some applications of that? So,
thank you. So yeah, today I'll give you a little bit of everything. I'm going to introduce what is the current state of the art in bit precise reasoning. I will tell you what is challenging about this, and I will also introduce a technique that we presented last year at CAF that addresses some of these challenges. And the spoiler is not all of them, but a lot of them. So, but before we get started, maybe let's establish the context here. So when I talk about bit precise reasoning, this is in the context of satisfiability modulo theories. So the problem of deciding satisfiability modulo theories, or SMT in short, is deciding the satisfiability of a first order logic formula with respect to one or more background theories. So this means we have theory symbols of that background theory. They have a fixed interpretation. This allows us to combine Boolean reasoning with domain-specific reasoning, and this is more expressive than SAT. Also, very often way harder, which is probably like kind of clear from being more expressive that it is harder, but I just want to flag this here. So in this talk, I will focus on the theory of fixed size bit vectors. I will introduce the theory in more detail in a bit. Just to give you a flavor, how a formula in SMT for the theory of fixed size bit vectors looks like here on the bottom. We have an uninterpreted bit vector symbol x. We have Boolean connectives, we have equality, and we have, I hope you can make this out clearly, the blue symbols are our theory symbols. So what this formula says is if x left shifted by 1 is signed greater or equal than 0, and x unsigned less than 4, and x times 2 modulo 3 is x plus 1. So the question is it satisfiable? I already kind of gave you the answer here. It is. And it is satisfiable if x is 1. So this is our model for this formula. So the theory of fixed size bit vectors provides bit precise semantics. So what is the main difference here when you consider the reals or the integers? We have a finite domain, and the semantics are different because the semantics of arithmetic operations are defined modulo 2 to the power of the bit width. So this is the main difference to the reals and the integers. So what does that mean? For example, this formula, when a is greater than b, then a minus b is greater than 0. This is true for the reals and the integers. However, for the machine integers, this is a different story. It's very easy to come up with a counterexample here. For example, for 8-bit integers, a counterexample is when a is 127 and b is minus 128, which would be the maximum and the minimum value in the range that you can represent. Well, a is greater than b, but if you negate minus 128, it remains at minus 128 because of an overflow, and thus we get that a minus b is minus 1. So to give you a more formal definition of the theory, so as the name implies, a bit vector is a sequence of bits of a fixed length, and we have bit vector constants. We represent them as either here binary strings or in decimal with the bit width attached. We informally call them bit vector variables. They are uninterpreted bit vector symbols. We have bit vector operators, like a plethora of bit vector operators. We have predicates. So we saw a couple already. We have unsigned, less than, signed, greater than, unsigned, less or equal, and so on and so forth. We have bitwise operators. So we have bitwise negation, we have and, or, XOR, and so on. We have shifts left, right, so logical right, and arithmetic right, and rotate, which wraps around. So literally, when you rotate bits, so shifts bits out of the range, right, and rotate wraps around. We have operators that I like to call word operators. So those are operators that manipulate the bit width. For example, concatenation, when you concatenate two bit vectors, extraction, when you extract the bit range, zero extension, and sign extension. So zero extension extends a bit vector with a given number of zeros, and sign extension extends it depending on the value of the sign bit with either ones or zeros. We also have repeat, and then we have arithmetic operators, all the ones that you can think of, actually. And overflow predicates for arithmetic operators. I already mentioned this. We have to consider overflow semantics here, which makes reasoning in this theory a little bit more complicated. They are a natural representation for machine integers and hardware registers, and they are therefore widely used in hardware and software verification. So a couple of side notes on semantics in this theory. So when we represent a bit vector, we usually put the least significant bit as the rightmost bit at index 0, and the most significant bit as the leftmost one. Bit vectors don't have a notion of signedness, but they can be interpreted as signed or unsigned. So if you interpreted them as unsigned, the value ranges from 0 to 2 to the power of the bit width -1. So for example, from 0 to 15. And then in the signed case, it is from -2 to the power of n-1 to 2 to the power of n-1, yeah, whatever. This is the signed range. And this means signed versus unsigned interpretation. If we have a bit string 1, 1, 0, 0, the unsigned interpretation is 12 and the signed interpretation is -4. Conversely, what this also means is if we have a bit string, a bit vector, and we want to get its negation, we do this via 2's complement. So for example, here, if we have 1, 1, 0, 1, in signed interpretation, this is -3. When we negate it, 2's complement, first invert all the bits and add 1, we get 0, 0, 1, 1, which represents 3. So just some overflow examples for arithmetic. If we have bit vectors of size 4, 8 plus 11 is 3, 8 times 2 is 0, -8 divided by -8 is -1 is -8. So all these three cases represent overflow cases. An important note in the theory of fixed size bit vectors as defined in SMT lib, division is a total function. We don't have partial functions in that theory. What that means is if A is divided by 0, it's defined as not 0 or ones. So we call the string that the bit vector with all ones, ones, okay? And correspondingly, if we have A mod 0, it is A. This is just how it is defined in the theory, and it corresponds also to how this is usually handled in hardware. So the dominating state-of-the-art technique for solving quantifier-free bit vector formulas in SMT is a technique that we call bit blasting. So bit blasting is an eager reduction to SAT that is combined with aggressively applying simplification techniques before the reduction is sent to a SAT solver. So a common bit blasting pipeline of an SMT solver can be seen here on the right-hand side. So our input formula is first simplified, then it goes to the actual bit blasting step, which means we translate the bit vector formula to an intermediate bit level representation, a circuit representation, and this representation is converted into CNF. This CNF is then sent to the SAT solver. This incurs a significant, potentially significant increase in size, hence the name bit blasting, but it is surprisingly efficient in practice. This is mainly due because state-of-the-art SAT solvers are surprisingly efficient. And it is the main technique in pretty much all of the state-of-the-art SMT solvers. When I say it is efficient in practice, the asterisks here is until it's not, but we will see when it happens. So to just briefly explain what we do in these separate steps here in the bit blasting pipeline. So when first in the simplification step, we basically we do two kinds of simplifications: local simplifications, so term rewriting, and global simplifications. So an example for a local simplification is a plus 0 can be rewritten to a, or a times 0 can be rewritten to 0. These are the most simple examples that you can think of. There are hundreds of more. So SMT solvers usually literally implement hundreds of rewrite rules for the 3 bit vectors. And this is done usually as the very first simplification. And then we apply the global simplifications in form of what we call pre-processing passes. Every solver implements different kinds of pre-processing passes. Usually one that is common across, I would claim, all the solvers, everybody implements this, is a technique that we call variable substitution. So what this does is given here. So if we have a variable a and a term t, and in our formula, we have the occurrence that a is equal to t, then we substitute every occurrence of a with term t. This is one of the simplifications that we do. It is a very important one because this actually can very drastically simplify the formula. So in the next step, in the bit blasting step, we translate our bit vector problem that has been simplified into an intermediate bit level representation. So why, you might ask, why into an intermediate bit level representation? So the reason is that what we want to do is when we simplify, so when we translate the simplified formula to SAT, in the meantime, what we want to do is, if we can, simplify as much as possible on top of the word level simplifications. So we want to preserve the hierarchical bit level structure before we flatten everything to CNF. And we do this typically with different kinds of representations. The most common one is called AND inverter graphs. It's implemented in pretty much all SMT solvers that have a focus on bit vector reasoning. So VX is the exception here because this also is a solver that specializes in bit precise reasoning, which uses X or NOT graphs. And then CVC5 and C3, which are general purpose SMT solvers with support of pretty much every theory that is currently standardized and more. They both B plus to an arbitrary Boolean structure. So all of these representations allow simplifications. They just target different kinds of simplifications, and people kind of don't necessarily agree which one is best. I would say an inverter graph. So if you ask me, AIGs, because this is a natural representation for bit level circuits, and it allows very efficient simplifications. I will get into that a little bit in a bit. What I want to stress here is the bit level representation can get very large. We need an efficient and compact representation for this. So this is super important. So AIGs as my representation of choice, so to speak, but not only mine. What are they? They are directed acyclic graphs over ANDs and negation, Boolean AND and negation. So the nodes represent AND gates. The negation is represented as an edge attribute. So as an example here, we have two AND inverter graphs here. This one represents A or B, and this one represents A, X or B. So we have A and B here. On the bottom are the input bits. The boxes and the blue labels, doesn't matter why we represent it like this. This is the input. The nodes are the circles, the ends. And then we have these bullets here, which are edge attributes. So what this basically says, A or B is represented as not A and not B. Yes, so they are not important for you to understand the graph. but they are important if you want to encode this to SAT. So these are basically the IDs. So this would be, if we encode this to SAT, then this bit would have CNF ID 2, and this one 4, and this one 6, and so on. Yeah. So in order to keep AIGs compact, we use structural hashing. So yes. You can directly map this to hardware. Yes. Yeah. So we perform structural hashing to detect and share identical subgraphs. So if we have an AIG that represents A or B, and it occurs somewhere else again in the formula, we don't want to duplicate it, right? That's what that means. So this representation is very compact, scalable, and as I already mentioned, it allows us for very efficient simplifications. So to give an example, how the bit blasting step actually proceeds. So here we have a formula, A plus B is less than C, all of bit width 2. And what we do is we do a post-order traversal, we traverse down to the leaves. We first translate A and B into 2 bits, each A1, A0, B1, B0. Then, so for the sake of simplicity, I do not use AIG representation here. I use XORs, but you have seen how they look like as AIGs, right? So the addition here, the least significant bit of the addition is represented as A0 XOR B0, and the most significant one as A1 XOR B1 XOR A0 and B0. So this is our addition. Then we translate C into 2 bits. So our predicate here, our unsigned inequality, has a single bit, which is represented like this, and then we put everything together. So this is our Boolean bit level representation of our bit vector formula. And this now gets translated to CNF by a Tatin transformation. And I'm not sure if this was covered on Tuesday, but so Tatin transformation is a very efficient way to convert an arbitrary Boolean formula to CNF. In our case, we only have AND gates. So we introduce a fresh Boolean variable for each AND gate, and then this is represented with 3 clauses in CNF. And this CNF is then sent to the SAT solver, and the SAT solver tells us SAT or unsat. So some of you may already see where the problem is here. Why we run into the issue that it is not always efficient. I have hinted at it already, but let me illustrate it. So this is the AIG representation of a 2-bit multiplier. So A times B. We have the 2 A bits, the 2 B bits. Those are our output bits. 6 AND gates doesn't look too bad, right? This is when you increase the bit width to 8. This is when you increase it to 16, and this is 32. And 32 is not considered a large bit width. And this is what the SAT solver has to deal with for a single multiplication of the formula. So this can get very large, very hard, very quickly for the SAT solver. So that is the main reason why bit blasting does not generally scale well with increasing bit width. So this is especially true in the presence of arithmetic operators. So arithmetic operators are our problem here, because they translate to large and complex Boolean circuits, and this becomes a potential bottleneck for the SAT solver, and this can already become a bottleneck for bit widths as low as 16 or 32 bits, depends on how many multipliers or dividers and remainders you have in the formula. But it is also especially severe for applications that reason over large bit vectors. So for example, in smart contract verification, we have problems defined over 256 bits with heavy use of multiplication, division, remainder. Or floating point arithmetic is very often reduced to bit vectors for solving in SMT. So we call this word blasting. So there, for a 64 floating point multiplier, the bit vector representation is 106 bit. We also have this problem in cryptography, for example, so when you have problems that encode translation validation of zero knowledge proofs, 510 bits. So this is an issue. And the question is, what can we do? So one avenue is to try to come up with alternative approaches to bit blasting. There have been a lot of attempts in the past to varying degree of success. Generally, all of these techniques that I'm going to show you here are complementary. None of them can, in general, compete with bit blasting, but they have their strengths and their weaknesses. So the first one is maybe a kind of natural idea. Why not translate this to integers? The problem to integers. Integer arithmetic in SMT is generally not as problematic as in the bit vectors. However, what is problematic in integers are bitwise operators, especially. So bitwise operators are encoded in a way that if you don't have a way to natively handle them in SMT, they blow up your formula. And nonlinear arithmetic, if you fully translate a formula to the integers, then you translate it to nonlinear arithmetic, which is also not always very efficient in SMT. So the procedures are not very efficient. Another approach has been so two different attempts in two different solvers, one in CVC4, one in MathSat, to try to layer cheap procedures before giving up and bit blasting as a fallback. A third one is an approach that is called MCSAT. I'm not going to go into detail what this is exactly, but think of it as more literally trying CDCL SAT solving to the SMT level. Local search approaches are actually great fast procedures, but only for satisfiable instances. So we don't have a way to deal with ansat here. And then a more recent approach called polysat is implemented in C3. And this is a technique that tries to have a native theory solve of nonlinear bit vector polynomials. So the question now is, do they scale any better, actually, than bit blasting? And so for this, we made an experiment. We randomly generated 500 term and formula equivalences for bit width 4 using CVC5's syntax-guided synthesis. It's not so important what that actually is. Think of it as you have a grammar, you define a grammar, and then a tool automatically generates these equivalences for you. And we restricted the occurrence of arithmetic operators to a single kind per equivalence. So since those are equivalence checks, what that means is for 4 bits, all of them are ansat. As you can see, we instantiate them with bit widths up to 8,192. And as you can see, those equivalence checks are not all of them are SAT for any bit width. So that true for any bit width. So that's why we have a couple of SAT instances here. Okay. So first, let's look at bit blasting. So we ran our SFT or bit blasting engine on those instances. We have 1,500 in total. As you can see, for 16 bits, we can solve almost every benchmark. And then when you increase the bit width, so scalability goes from 99% to 49% solved instances, which looks kind of bad, right? But if you look at the other approaches, the picture is actually worse, which is interesting, right? Because you would think, well, they should be kind of orthogonal. They should have maybe more stability. Well, that's not necessarily the case. So the lazy layered approach in CVC4 goes down to 13% even. And CSAT anyways only fully supports a fragment and has to resort to bit blasting in yikes, but goes down to 33. Int blasting, 26%. Polysat looks a bit more stable, but this is actually not the full picture. So almost 500 instances that Polysat can solve are actually solved by rewriting in C3. And so Polysat just struggles in general on those instances. So when we we try to determine how orthogonal they are. Do we actually gain anything with any of these instances? Yes, we do. That's the good news. So if we compute the virtual best solver here, which means, so we pick the best result for each instance, we go from 100% to 66. So some of these approaches can solve instances that the others can't. That's what this means. Okay. So another avenue to tackle the scalability problem is to improve scalability of bit-blasting itself. There have been attempts in the past. They are not as widely implemented, mainly due to some technical issues, I would claim. So the first one is under-approximation. So under-approximation, you can think of as you try to restrict the value ranges of the input and try to find out if it is unsatisfiable, and if it's unsatisfiable, then no, if it's satisfiable. If it's satisfiable, then you know you found the model for the formula, for the input formula. But if it's unsatisfiable, you have to increase the bit width. And so this can help. It was implemented in Euclid first, and I think in Bolector and in STP. Euclid also introduced a first version of abstraction to more lazily handle, so for a more lazy bit blasting approach, but a very naive one, which is given here, where multiplication was abstracted with a partially interpreted function that is given here. And if that was not successful, immediately Euclid fell back to bit blasting. We try to tackle this issue more comprehensively with an approach that we presented last year at CAF, where we propose a counterexample guided abstraction refinement style framework that is used for lazily handling multiplication, division, and remainder. And this framework is implemented in our solver bitpuzzler, and it significantly improves the performance on large bit vectors in the presence of these arithmetic operators. So see, counterexample guided abstraction refinement is a very common paradigm in formal verification, formal methods. So the secret sauce actually lies here, how we define our abstraction refinement scheme for these operators. And we came up with 70 lemmas in total. I will explain this in more detail in a bit. We also decided to be a little bit lazy and not come up with all of them manually, because this is tedious. And we devised a way to be able to tell if a lemma is actually good or not. But let me start with the general CEGAR abstraction refinement loop, how we have it integrated in our framework. So given a set of input assertions, what we first do is we abstract each occurrence of multiplication, division, and remainder with a fresh symbol. So what this means is basically, you can think of literally replacing every multiplication, division, and remainder operation that occurs in the formula with a fresh bit vector variable. So this is an over-approximation of the input formula. And this abstraction, we then send to the bit vector solver, the bit vector solver that does bit blasting. Since it's an over-approximation, if this is answered, we're done, we're good. If it's sat, we get a model back. And now we have to check if this model is consistent with the true semantics of the operators that we have abstracted. If it is consistent, great, we're done. If it's not consistent, we refine the abstraction with lemmas. That is the basic idea. And we do this iteratively until we converge to a consistent model, or say answered. So this refinement step works as follows. So for each abstracted term, we first check if it is consistent, which means if we have, for example, a multiplication x times s, which is abstracted with the term t, and the bit vector solver gives us as a model x is 3, s is 6, t is 1. Well, this is obviously not the case for 32 bits. So this is inconsistent, because 3 times 6 is 18 and not 1. So then we check if so we have a predefined set of lemmas. If we check in order if a lemma is violated under the current assignment. If so, we add a single lemma for this abstracted term to our set of refinements and then continue checking the other terms. We do this in order. So we have a refinement scheme that defines lemma tiers, 4 in total, and we process those tiers in order. Our main tiers are those two, tier 1 and tier 2, which contain our statically defined lemmas. And the rest I will explain in a bit. So the reason why we only add a single lemma per abstracted term is we want to be super lazy about this. We don't want to overwhelm the Satzhover. So that's why we don't add all the violated lemmas, just the first one that we encounter. So our first tier consists of what we call handcrafted lemmas. It's basically the ones that we came up with. And we have lemmas here in 2 categories. The most important one is lemmas that describe properties by an invertibility condition. So what is an invertibility condition? So an invertibility condition basically states, given, for example, x times s is equal to t, is there a value for x given s and t? That's what the invertibility condition states. It tells you if you can compute an inverse value for x, okay? For example, the invertibility condition for x times s is defined for x as minus s or s and t is equal to t. Symmetric for the other side. What does that actually state? It states that x times s must have at least as many trailing zeros as x or s. So here's an example where we have trailing zero means on the least significant side. So for example, if t is 1, 1, 0, 1 trailing zero, s is 1, 0, 1, 0, 1 trailing zero, so it's at least as many, right? We can find an inverse value, 1, 1, 1. Okay? On the other hand, if this is not the case, which is this right-hand example, we can't find an inverse value. That's the intuition behind it, okay? The other bucket of lemmas in this category are just encoding basic properties of the abstracted operator. For example, that t must be odd if x and s are odd, like very basic properties. And we also verified the correctness of these lemmas up to bit width 512. So we have 17 in total for all the arithmetic operators. So our second tier consists of synthesized lemmas. So as I already mentioned, we got very fed up with sitting down and thinking hard about lemmas, and then we decided to try to do this in a more automated fashion. And what we do here is we utilize the syntax-restricted abduction engine of CVC5 to automatically synthesize lemmas for us in an offline fashion. This is an important detail because this is kind of an expensive process. So how is abduction defined? Abduction is defined as if you have two formulas A and B, find the formula C such that A and C implies B is valid and A and C are sat. So we find lemmas using this in a way that so that we have that T and not lemma implies the negation of our literal. So our A and B are true and the negation of X op S is equal to T. So these details are not so important. It's just a nice trick to be able to use the abduction engine to generate these lemmas. And for example, for multiplication, one of the lemmas that we get is this one. Don't ask me what property this actually encodes. Most of them are not very intuitive. So you have to really sit down and think about it, and then it's maybe just some corner case. It's really not intuitive, which also shows the strength of this approach because it is able to cover certain corner cases that you would not think of. So in order to not generate too many lemmas and redundant lemmas and lemmas that do not actually improve our approach or our technique, that just would just hinder them, we decided we need a way to be able to tell how good a lemma is. And we do this by defining a lemma score. I will talk about this in a bit. And we filter them based on the score with respect to our handcrafted lemmas. So our third tier is kind of a last fallback strategy before we have to give up for this particular abstracted term. We call these value association lemmas. What that does, so what they do is they rule out the current inconsistent model values. So for the previous example, what we would do is we would add x. If x is 3 and s is equal to 6, then t must be 18. We only do this if none of the lemmas in those tiers are violated. And also, we do this in a very limited fashion because we don't want to start enumerating all the model values. So we limit this to bit width by 8 instantiations per term, so which means 4 instantiations for a 32-bit term. This is just based on the current model value. So that is actually what the bit vector solver currently gave us back. So x is 3 and s is 6, and then we evaluate the value and add that it must be 18. Yeah. So our very last resort is basically we have to say, okay, we give up for this term. We add a lemma that enforces p-blasting for this term. So I don't know if this is very visible. It's not so important. This is our set of lemmas. I want to highlight our invertibility conditions here in red. They are our strongest lemmas. I also want to highlight that we don't have one for UDIF. And the reason is that the invertibility condition for UDIF introduces a division, which we cannot allow because this would potentially cause non-termination of our procedure. So that is the reason why we were not able to include it. And we need, as you can see, way more lemmas in order to get close to the same performance in terms of lemma score as the other two. So lemma score, very important point. This is a metric for the quality of a lemma. What we do here is we basically evaluate a lemma over all the possible value triplets of x, s, and t and count how many are true. So for example, if you have x times s for bit width 4, the worst case would be the combination of all possible values, which is 4096. And the best score would be the combination of the values for x and s, which is 256. So we visualize this here as the black circle is the worst possible score, red circle is the best possible score. And what we now try to do, so this is the intuition behind our lemma scheme, is what we want to do is with our lemmas to approximate the red circle as closely as possible. So those are the scores, the individual scores for the lemmas for multiplication. So the lower the better. This is our invertibility condition. And in combination, this brings the score down to 704, which means that this rules out 88% of the triplets already with these four lemmas for multiplication. And if we add our synthesized lemmas on top of that, we bring this down to 94% for multiplication, 96 for division, and 96 for remainder. Which means this already rules out a lot, almost everything, right? But the diff, that is the tricky part. What we are still missing, that is the tricky part. So let's get back to the question about scalability. Now the question is, how well does our approach actually fare in comparison? And as you can see, our technique on this benchmark set bumps this up to 85%, from 49% to 85%. And we bump the virtual best solver to 88%, which is great. So just a couple of results to give you an idea. We evaluated our approach comprehensively, but I want to highlight a couple of benchmark sets that are of interest. This is the benchmark set that we already saw. So the blue line is bit bootstrap with bit blasting. This red line is abstraction. And you can see, so the higher, the better. There is a significant bump in solved instances and also improves significantly in terms of solving time. Here we have a benchmark set that comes from smart contract verification. Similar picture, red line way above the blue line. And as a reminder, this is over 256 bits. Here we have a benchmark set that encodes translation validation of zero knowledge proof, so a cryptography application. And here you can also see we pretty much more than double the number of solved instances. So for this particular set, actually in blasting was originally better, but we outperform it significantly with our approach. And what is also important to note is, well, memory usage is very often also a concern, right? And as you can see, so the blue one, again, bit blasting, the red one is our abstraction approach. This is in gigabytes of memory as a sum total over the benchmark sets. We significantly decrease the memory consumption with our approach. What is also a couple of things that I want to just highlight here. What is interesting to note is that 80% of the instances that we solve are solved without bit blasting any abstracted terms. So what that means is, for those, the full specification of the arithmetic circuits is not necessary. Then what is also interesting to see here is, so what this indicates is how many instances added lemmas in tier 1, tier 2, tier 3, tier 4. One might think that our value instantiation lemmas are worth less because how much would they help, right? I mean, it sounds like a stupid idea. However, as you can see, they do actually significantly help. So for example, on the Sartora set, we have 60.4 instances that get until tier 3, but only 13.3 actually have the bit blast terms. So this is really interesting. For the 20% that required bit blasting, only 37% of the multiplication, 13% of the division, and 2% of the remainder terms were actually bit blasted. And one also not so unimportant detail is we don't need many refinement iterations in order to come to a conclusion, right? So on average it's 37, but the median is actually 4.
I suggest that it might be a good idea to actually do the instantiations first, and maybe they're so powerful.
I would argue no, and the reason is because what you do with this, you just rule out a single point, and our lemmas, they cut off like large areas, and then, as I mentioned before, we have this diff that we do not cover, right? And very often those instantiation lemmas, they cover some points in that diff that don't, yeah, and that really helps us. That's the reason why this really helps us. If we start doing this way earlier, then we would just start hand-picking single points, but we actually have the opportunity to just cut off more, right? And then you really do not want to do this very eagerly because you just get lost in the woods, basically, right? Yeah. So now the interesting question is, so have you solved scalability in bit vector reasoning, the problem of scalability in bit vector reasoning? Unfortunately, the answer is no. I mean, we solved a lot of issues, but the problem is that as soon as you need the full specification of the arithmetic circuit, you're out of luck, because then you will have to go to bit blasting. So basically, what is still challenging is everything that involves verifying if an arithmetic circuit plus whatever, something is correct, for example. So if you have equivalence checks of this form. So this is the most simple example that you could think of is, if you have A times B is not equal to B times A, if this is answered, then this is correct, right? This is true. So I made an experiment. I switched off all the simplification techniques in bitWurzler and started instantiating this for bit widths up to 13. This gives us how many variables does the CNF have, how many clauses does the CNF have, how much time do we need in solving, and how this is the size of the proof. the direct proof for the problem. And as you can see, this grows very quickly and looks like exponentially, right? And indeed, arithmetic circuit verification is known that this is very hard for SAT solvers. And this indicates that for this particular problem, we cannot find short proofs. This correlates with the solving time, right? I mean, just as a side note, this is super easy for SMT solvers because we just rewrite this, right? We rewrite commutativity, immediately see that this is that A times B, this equal A times B must be answered, and they're done, right? However, what if we start mixing this up a little bit? What if we start combining this with bitwise operators, for example, in a way where current SMT solvers, so none of the current SMT solvers can simplify this. And this is answered. So those two terms are equivalent. And I can give you a manual proof for that. Do SMT solvers give us a proof for that? No. None of them can. For the small bit widths they can, but not for larger. So for 16 bits, for example, all of the approaches that I showed you before, time out after 60 minutes, if you enumerate this with the C++ program, you're done in 30 seconds. So we do have an issue here still. And it does imply, first of all, that SMT solvers still maybe don't sufficiently well enough reason on the word level, right? But the question is also how to solve this. And this is still an open problem. So what are the takeaways? What do I want you to take away from my talk? Generally, SMT for the theory of fixed speed vectors is a very powerful tool for a lot of application in formal methods. Large speed vectors with arithmetic are challenging. It's always good to know what is challenging for a technique that you're using, right? Usually arithmetic always occurs in combination with bitwise shift word operators in real problems that we see, because they usually stem from software verification, hardware verification originally. And that's why they are never purely arithmetic. And so techniques like in-blasting that excel at purely arithmetic problems, for example, they just really struggle as soon as you combine them with anything else. What I also want you to take away is scalability is an issue for every technique. So know the technique that you're using and know which tool to use for which problem, right? Blasting is still the best performing approach, which is also really interesting, right? But the other ones are complementary and they have their value. And our abstraction approach actually really significantly boosts the scalability of blasting. That is basically the main takeaway that I want you to go home with today. And the main reason for this is because for a majority of solved instances, the full arithmetic circuit is not required. So the people who will very strongly say, this is not true. For example, people at EDA companies, because they need actually that we can verify the correctness of an arithmetic circuit. And here we still struggle, right? So that is all from my side. I'm happy to take questions.
You mentioned that you only apply one lemma at a time when you're doing the refinement. I was wondering if you tried like top K with your lemma scoring technique, or if there's like already evidence that one lemma at a time is the best.
So we played around with this actually quite a bit. So we tried to be more eager, and in our experiments it shows that you want to be as lazy as possible, because the problem is that in our lemmas we don't have any occurrence of multiplication, division, and remainder, but we have addition. Addition is not as expensive as the other three, but it's still not cheap. So what you don't want to do is overload the SAT solver with things that are not strictly necessary to come to the conclusion. And especially for large bit widths, if you have, for example, if you have many adders, this still adds up, and this can become hard for the SAT solver very quickly. So that's the reason why you want to be as lazy as possible.
Thank you.
So, of course, One of the things that I think you also looked into it, right? Some others did as well, but the challenge is, so you have your manual proof for the example that you showed, which is a couple of slides before. How far are we from trying to get from proofs for small bit width that we can generalize? Right? Because I think this is a key challenge that needs to be overcome, right?
I mean, how far are we from
being able to find short proofs for small bit width and then generalize them for arbitrary bit width?
That is actually an excellent question, and it is hard for me to answer for two reasons. So first of all, I'm super optimistic that we can, and we are currently working on this. How far away are we? I don't know, to be honest. So it is a long road, and I have no idea how long it is. But we have some intuition, some ideas for what we can try, but we are currently rather in the early stages, so to speak.
You had a paper about this 5 years ago, right? So on this theme, on generalizing sort of bit width independent.
Yes. So that is a very different kind of a hard topic, I would say. I think the conclusion back then was, well, we are still kind of far away. I would argue our recent submission should bring us closer, but yeah, for this particular problem that I had on the slide, yeah, of course, you want to, I mean, there are a lot of things that you want to prove in a bit width independent way, right? But I mean, my point is, even if you don't do this in a bit width independent way, I mean, for 16 bits, we are already, yeah, giving up, basically, right? So this is a whole different kind of problem, maybe. It's a bit orthogonal, but yes, I mean, I don't know. It's a good question. I don't know. Is my answer, I guess.
Okay, thanks.
I can jump in.
Yes.
So those of us who care about applications to mathematics, are thinking, okay, so how can we use this? And so one thing is, there may be mathematical problems that can be reduced to bit vector. But it seems to me that this general, CEGAR and this approach of, you kind of abstract away the hard parts and then you selectively add in levels.
Yes.
That seems very good.
Yes, absolutely. Yes.
Okay, so
yes.
Any thoughts on like apply this to other domains or just if you go to a domain, try it.
It is actually this abstraction refinement idea is very pervasive everywhere in formal methods. So because very often the problem is that if you give the full, let's say the full specification of a problem to a verification tool, it will just die on here. So and you try to make it easier, right? There are a lot of ways to do this. I mean, one obvious one is, for example, to try to cut off stuff that you don't care about, right? This is kind of, it's always like you try to remove stuff that you don't care about, right? That's just the basic idea. You can apply it, I would say almost on everything, but the really difficult part is how do you actually refine it in a way that you then can still get to a solution, right? So that is the really tricky part. But generally, I would say this is a concept that can be applied to many, many applications. And you have to think about it in a way, so what do I care about in my problem and what do I not care about? And let's maybe try first without the stuff that I don't care about.
It's a general mathematical strategy, trying to prove a theorem. When you try to abstract
yes.
something more general, and when you fail, then you can.
Yes, exactly.
Thank you. It's interesting. So I guess my question is, maybe I just didn't catch this, but I didn't understand how you found those lemmas in the first place that you're doing the refinement. And then also, I guess this is the follow-up to that, is as you scale to, say, 64 bits, 128 bits, does that change the lemmas, or do you have any sense of that?
Yeah, so, let me see. I'm not going to get full into the details what this framework here does specifically component per component, but think of it like this. So first of all, the handcrafted ones, we just sat down and thought about it, right? And then what we did is, so CVC5 has a way, so CVC5 is an SMT solver, but more than just an SMT solver. And CVC5 has a way to give you, to randomly generate formulas for you based on a grammar and based on the problem definition. Our problem definition that we utilized was abduction. And so we asked CVC5 to give us a term, not L, such that, for example, X times S is not equal to T. Yeah. And what this does, what then CVC5 does, it starts enumerating terms. Yeah. And we did this like in an iterative fashion. And then we computed the score of each lemma. And then we computed the score in combination to the lemmas that we already had. And only if it improved the score, we added it to our set of lemmas. And then we continued. And that's basically how our automatic generation of lemmas was done. Does that answer your first question?
Yes, yes.
Okay, cool. So do the lemmas change with increasing bit widths? The lemmas themselves not, but the terms have a larger bit width. I mean, most of them, no, all of them are actually bit width independent. So you have some where you extract, for example, the most significant bit. So what would changes at which index you find it. But other than that, the lemmas themselves don't change. It's just that the bit width of what occurs in the lemmas changes.
Well, so presumably there are lots of people using your software. You get reports back from them saying like what kinds of queries they're using, and then you compile like which ones are bad to study.
Yes, that's basically what not only we do, but we as a community in SMT do. So SMT solvers have as input language a language that is called SMT-lib, but SMT-lib is also an initiative that maintains a benchmark repository. And each year we collect real instances of users to add to this repository. And they come from all kinds of applications. I mean, some we can't. So sometimes we get applications, benchmarks from users that we cannot make public because of IP concerns and whatever. But in general, so I'm also part of the SMT maintenance team, and we are really pushing people also to submit their benchmarks, because this is the only way for us to improve our tools. If we get instances where our solvers struggle, and actually our abstraction based approach started with a set of benchmarks from smart contract verification provided by Sartora, where they were like, guys, we really want to use this, but we can't because you just can't solve it. And that's how I started.
It was sort of the two-part question, and then the second part was the one I really wanted to ask was, do those significantly differ in some aspects from randomly generated?
Oh, yes. Yes. So,
and you understand
so the main difference, I would say, between randomly generated ones and benchmarks that come from application is structure. So benchmarks from applications have a lot of structure, and very often SMT solvers can utilize this structure. This, I would argue, is mainly important. So in the case of bit blasting, it's mainly important in the simplification stages. So there we really try to make use of structure for simplification purposes. For our abstraction-based approach itself, I would say it does not help us that much. Yeah.
I mean, this is a nice question, because that suggests if we want to further automated reasoning for mathematics, we do well to have these repositories of contributed content.
Oh, yes.
Well, the reason why I asked was, based on my talk yesterday, is what happens is if you type in a walnut query that's based on like a theorem or a conjecture or something, it runs quickly, but if you slightly make a mistake in your translation to first order logic, it takes forever.
Mhm.
And I think it's precisely because what people are interested in has structure.
Yes. But we're always happy to get such instances, because that is actually what drives our research, basically. Yeah.
So let's thank Aina